Most people learn that water boils at 212 degrees Fahrenheit. But that's only true with standard atmospheric pressure. Lower the pressure surrounding the water and its boiling temperature drops. With a strong enough vacuum, you can boil water without heating it at all. So today we're testing it with 3 different samples. Room temperature water, refrigerated water, and water chilled with ice to nearly frozen. Will all 3 boil inside this inexpensive home vacuum setup? And exactly how much pressure will each sample require? Instead of trusting just the mechanical gauge, we built a sensor setup. Boiling happens when the vapor pressure of water becomes equal to the pressure surrounding it. At a standard atmospheric pressure, which is about 1013 hectopascals, pure water boils at 212 degrees Fahrenheit. That's the boiling standard, which I actually already have showing on that display. Right now, because we haven't pulled the vacuum or anything, you can see at the very top, our actual pressure is 965.1 hectopascals. So we're already, expected boil, 209 degrees. We're already a little bit below standard boiling temperature. So as the vacuum pump removes gas from the chamber, the surrounding pressure is going to drop. We're going to see that over here on the display from those sensors. So, for instance, if we can get that top number to say something like 80 hectopascals, that should have a water boiling temperature predicted at about 106 degrees Fahrenheit. As you can see from this display, it says water temp 89.2. That is this water here. That is room temperature. So what we're going to use as our main pressure sensor is that long one there with the red light on it. That is an MS5611 absolute pressure sensor. It's rated to measure between 10 and 1200 hectopascals, which should give us enough range for a home vacuum chamber. Below that, that little purple one is a BME 280. That module measures air temperature, relative humidity, and a second pressure sensor. That one only goes down to 300 hectopascals, but we're using it kind of as a backup here, just to see. Then inside there, you can see the little white box where it's connected, and it runs out through the lid and to the cup of water is our DS18B20 probe. This is measuring temperature. It's just a water temperature probe. And then inside there, we have an ESP32 that is sending to that ESP32 using ESP-NOW. So on the display that we're always going to monitor with the P950 zoomed in on it, we have the MS pressure, that's the pressure from the more sensitive module, the air temperature, which is coming from the BME, the density of the air in the vacuum chamber, water temperature, which is coming from this probe here, boiling standard, that's the standard temperature of boiling water, expected boil is what it should boil at using the pressure from the pressure sensor. The margin is the difference between the water temperature and expected boiling. And then we have the air density, 97.7%. It's got a slight vacuum happening just because of the way I set it up. But that's not that's not an important thing. So before starting, we're gonna make some predictions. At room temperature, the sample that we have here, was it 89 degrees? We should get that boiling at like 40, maybe, hectopascals. The refrigerated one, we'll have a refrigerated cup of water, which should be about 40 degrees. That should be around 8 to 10 hectopascals, which is slightly below the MS reading. So that we should see kind of an issue with, where it's not gonna give us the exact measurement. And then ice water is really just to test if we can pull enough of a vacuum to boil ice water. Test 1, room temperature water. We've got our cup of water in there, the lid is on, the vacuum pump is set up, and we're reading 90 degrees Fahrenheit for that water. So let's go ahead and start pumping out this air. We can see the air bubbles already starting to be pulled out of the water. Okay, there we go. It took a little over 10 minutes, but we finally have a rapid boil. So it looks like we're at about 45 hectopascals right now. At that pressure, it exceeds the boiling point. If you look there, we are about 1.5 degrees warmer water than the boiling temperature that air pressure should allow. So we've gotten boiling water at 89.5 degrees Fahrenheit. So that took a little over 10 minutes. You'll see the timer when we did it on the test itself on the screen sped up through that time lapse. But I was going to do refrigerated water and ice water, but because that took more than 10 minutes to pull that vacuum for 90 degrees about, what I'm gonna do is we're gonna test 3 things. What we're gonna do is boil 3 different temperature waters. So the back cup here is our room temperature. It's about 86 degrees. This one here, we currently have at 110.7. And this cup here, it's sitting at about 120.6. It is slowly bouncing between 0.4 and 0.6. But we're gonna test all 3 of those. We can't fit all of those and all of our other stuff in there, but we will have 2 cameras recording. So we've got the GoPro with the straight down view, the Nikon over here with a side angle. We'll click this on. So the 120 degree water started boiling really quickly, but it's steaming up the inside of that container. While doing it, this is an interesting thing. So that started to boil first, pretty quickly, and then this like slowly stopped boiling as much, and this started boiling, and this just ended rapid boil, and the back one's like starting to boil. So I'm gonna have to figure out why the warmer water is now not boiling. Okay, this is pretty cool though. I'm not touching anything. It's just like big boiling in the front one all of a sudden. So it seems like at different pressures, different temperatures like start and stop boiling. But I don't know why the hottest one isn't boiling at all anymore. Unless just boiling it maybe rapidly cooled it. But that one's doing some cool big bubbles that you don't even see come from like inside. They just appear at the top. So that back one's going. It's been going for about 18 minutes or so. And you can kind of see that back one was boiling a little bit. We're gonna stop recording everything, open up this valve. Fun because the water boils like for a split second when you pop that valve. And then once we pull this off, I found my 2 aquarium thermometers. So we're gonna throw those. They're not as accurate as this thing, but let's just measure the temperature of all of the waters. These are kind of laid out in the way that they are. We'll give it a couple of minutes to get the proper temperature and then see what it comes up with. Okay, so the thermometers have been sitting in there for about 2 minutes, and I'm actually super surprised. So 99.3 degrees Fahrenheit, that's the one that started at like 120. Then here we have the one that started at around, 110 is 97.7. And the one that started at 85-ish degrees is at 95.9. So that's really interesting that they all cooled down to about the same temperature. Well, this one heated up, but they're all at about the same temperature, which I guess makes sense because I think pulling all that air out of here should put it to the same temp. But so after thinking it through, the starting and stopping actually makes a lot of sense. Each warmer sample began to boil first, but boiling caused rapid evaporative cooling. As the water cooled, its vapor pressure dropped, causing the boiling to slow or stop. Then as the pump lowered the vacuum chamber's pressure more, the cooler samples reached their boiling points. Those enormous bubbles were likely caused by the smooth glass providing only one or two good places for vapor bubbles to form. Under low pressure, those bubbles expanded dramatically, increasing what looked like one continuous giant bubble. Overall, the experiment clearly showed that the hotter water boils at a higher pressure, colder water requires a deeper vacuum, and boiling itself rapidly changes the temperature of the water pretty quick. Water doesn't always boil at 212 degrees Fahrenheit, it boils whenever its vapor pressure matches the pressure of the surrounding area. I thought this was a pretty fun experiment, and it gave us a great look at how pressure changes the temperature at which water boils. If you'd like to see more hands-on experiments and debunking of internet claims, subscribe to the channel so you don't miss the next one. Thanks for watching.